These are solutions to some of the exercises from the Discrete Dynamical Systems course 6G6Z3003. So first of all, we look at chapter 3, question number 7. And we're asked to determine the fixed points of periods 1 and 2 for this Henon map, and we also want to derive the inverse map. So for period 1, we want to solve the equations xn plus 1 equals xn equals x, yn plus 1 equals yn equals y. And from equation 2, straight away you can see that y is equal to x. We can substitute y equals x into equation 1, and we get this quadratic equation, which can be factorised here. So that gives us two fixed points of period 1. To determine the stability of these fixed points, we use the Jacobian matrix, dp dx dp dy dq dx dq dy, which are given by this matrix. We substitute the values of the fixed points, and we get these matrices, and we can find the eigenvalues using MATLAB. So these are the eigenvalues. If we look at the modulus of these eigenvalues, then you can see that both of these fixed points are saddle points, because one of the eigenvalues has modulus bigger than 1, and one of them has modulus less than 1. So it has an unstable branch and a stable branch. So both fixed points are unstable. So for period 2, we want to solve xn plus 2 equals xn, and that should be an x, and yn plus 2 equals yn equals y. So to find the formula for xn plus 2, we use iteration. So we replace yn with yn plus 1, xn with xn plus 1. And then we know that from equation 2, yn plus 1 here is equal to xn. So that's why that is xn. And then we substitute xn plus 1 into here, and we get these equations. And then yn plus 2 is yn is y, xn plus 2 is xn, and that should be x, and we get these two simultaneous equations. Again, we can solve these with MATLAB, and we get these two fixed points of period 2. To find the inverse mapping, from equation 2, we get an expression for xn in terms of yn plus 1. So xn is equal to yn plus 1. And then from equation 1, we now want an expression for yn. And if you rearrange equation 1, then we get yn is 10 over 9, xn plus 1, take away 3 over 50, and then plus xn squared. But as we've said, xn is yn plus 1, so that's why we have a yn plus 1 squared here. And now we've expressed xn and yn solely in terms of the xn plus 1 and yn plus 1, so this is the inverse map. Okay, next we go to chapter 4, and we're going to have a go at question number 2 from chapter 4, from the exercise in chapter 4. So here is question number 2. So given C is minus 1 plus I, we want to determine the fixed points of periods 1 and 2 for this mapping. So here is the mapping, Zn plus 1 equals Zn squared plus C, where C is minus 1 plus I. So again, to find the fixed points of period 1, we solve Zn plus 1 equals Zn equals Z. And that gives us this quadratic equation, which we can solve with MATLAB, and we get the approximate positions of Z11 and Z12 are these values here. Again, to determine the stability of these fixed points, we differentiate. So we differentiate f of z, which is this function here, which is z squared plus c, and we get 2z. So to determine the stability of the fixed points, we take the modulus of for those two fixed points, and you'll see for one of them we get 1.62, and because the modulus is bigger than 1, that's unstable, and for the other one, the modulus again is still bigger than 1, so this is also unstable. To find the fixed points of period 2, we want to solve Zn plus 2 equals Zn equals Z. So again, using iteration, Zn plus 2 is Zn plus 1 squared plus C, but we know what Zn plus 1 is, so we substitute that in, and you can see we get this quartic equation, which again we can solve with MATLAB. And if you solve this with MATLAB, then we get Z21 is this point, and Z22 is this point. So these are fixed points of period 2. And notice that the fixed points of period 1 also appear here, but we discount those points. Finally, we go on to chapter 5. So we're going to do exercise 3 from chapter 5, which is the Ikeda map problems. And question 3, we're asked to determine the inverse of an Ikeda map. So the question is here. So here's question number 3. Here's the Ikeda map, and we want to prove that this is the inverse map. So to find the inverse map, we need to express En in terms of En plus 1s. So if we rearrange this equation, you'll see that En is en plus 1 minus a. So we subtract a from both sides, and then we divide by b. And then we multiply both sides by e to the minus I mod en squared. But on the right hand side now, we need everything to be in terms of en plus 1, and we've got a problem with this mod en squared. So we need to know what mod en squared is. So we can use this formula, because if we take the modulus and square, then mod en squared is equal to the modulus of en plus minus 1, en plus 1 minus a over b squared times the modulus of this value. And if you take the modulus of this value, you get 1. So that's why that disappears. So mod en squared is the same as mod en plus 1 minus a all over b squared. So that's what goes in place of this expression. And now you can see that en is expressed completely in terms of en plus 1. So that is the inverse map. And then finally, for chapter 5, we're now going to have a look at question number 4. So we've got an expression here, which is a type of Ikeda map, and we want to show that this expression is true. So we can rearrange this formula, en plus 1 equals this, first by setting en plus 1 equals en equals es, and es stands for steady state. So en and en plus 1 both become es. We rearrange the equation to find a, and you'll find that a is es times this expression. Now to find mod a squared, using complex numbers, this is a times the conjugate of a. So here is a, here is the conjugate of a. So if you multiply these two together, es times es conjugate gives you mod es squared, and then if you expand these brackets out, you should be able to show that this is true. Okay, and then simply all we have to do then is rearrange this formula to find cos of phi minus c over 1 plus es mod es squared. And if you rearrange that formula, then you get the required answer. And that concludes these solutions to some of the exercises in chapters 1 to 5.